Okay, so today we are going to talk about stoichiometry. And so stoichiometry is just using a balanced chemical equation the same way you would use a recipe to determine how much reactant is needed to produce a certain amount of product. So for example, in this recipe, we're making 5 dozen chocolate chip cookies, and all of the requirements for making 60 chocolate chip cookies are listed up above, right, in the recipe. So you need a cup of chopped nuts, although I'm not sure if anybody actually adds those, a teaspoon of vanilla extract, 2 large eggs, a teaspoon of salt, etc., right? The question here over here says, you really wanted chocolate chip cookies, but you only had 1 egg, and assuming that you're going to keep all the ratios the same, how many cookies would you expect to make? And so if the recipe calls for 2 eggs and results in 60 cookies or 5 dozen cookies, then if you only had 1 egg and you had plenty of everything else, of course, we would expect to make half as many cookies, right? So you would expect to make 30 cookies, right? Because we're cutting our eggs in half, which means we're going to cut our product in half, right? Now, a chemical reaction is really no different. This chemical reaction says 2H2 plus O2 yields 2H2O. And those 2's, and of course implied 1's in front of the oxygen, just basically describe molecules, right? So this recipe, we can think of this reaction as a recipe that calls for 2 hydrogen molecules and 1 oxygen molecule, and results in 2 H2O molecules, right? So it is really just like a recipe, just like a chocolate chip cookie recipe. Only instead of dealing with cups and teaspoons and tablespoons, we're dealing with molecules. But molecules are really, really small, right? So it makes a little bit more sense if we're actually doing this reaction, we're making water, makes a little bit more sense for us to blow that up into moles, right? And think of that as being a mole ratio. So in other words, 2 moles of hydrogen is needed for every 1 mole of oxygen. That is a mole ratio. You could also write it as a fraction. So you could say 2 moles of hydrogen over 1 mole of oxygen. Or you could flip it around, right? You could say that 1 mole of oxygen is needed for every 2 moles of hydrogen. Those are both molar ratios that could be taken from this balanced equation. We could also involve the product, right? The water. So we could say things like, 2 moles of water is made for every 1 mole of oxygen used. All right, there's all kinds of different molar ratios that come from this balanced equation. All right, let's take a look at this one. It says, in order to produce 3 moles of water, how many moles of oxygen would we need? Well, we just said that we know that there is 1 mole of oxygen needed for every 2 moles of water produced. So we would need half as much oxygen, or we would need half as many moles of oxygen, and so half of 3 would be 1.5, right? So 1.5 moles of oxygen would be needed to produce 3 moles of water, okay? And that's basically what stoichiometry is. It's just using those ratios, okay? So let's take a look at a new equation. So same concept, different equation. It says, according to the reaction below, how many moles of dinitrogen pentaoxide would be produced if you used 7 moles of oxygen with excess nitrogen? So that word excess just means we've got plenty of nitrogen. We don't really have to worry about running out of nitrogen. So we're going to calculate our moles of our product, our dinitrogen pentaoxide, from our 7 moles of oxygen. So we're going to treat this like any other unit conversion. We're going to start with the number that we were given. So 7 moles of O2. We're going to put that over 1. And then we're going to try to cancel moles of O2. So it's going to go on the bottom of our fraction. Then the thing that we're trying to find says how many moles of dinitrogen pentoxide, so N2O5, that's going to go on top, right? And then we're going to use the molar ratio from the balanced equation. And the balanced equation shows us that we produce 2 moles of N2O5, so I'm just getting that from the coefficient, for every 5 moles, again, just coming from the coefficient there, of oxygen consumed. Okay? So this is just going to be 7 times 2 divided by 5. Okay, and if we plug that into the calculator, we should get about 2.8 moles of N2O5. So that's how much we expect using 7 moles of oxygen instead of 5, like the balanced equation calls for. We would get 2.8 moles of N2O5 instead of just 2. So the next question is, how many grams of oxygen would be required to produce 0.5 moles of N2O5? So go ahead and see if you can set that one up on your own. Go ahead and pause and see if you can do that one. Okay, so hopefully you maybe were able to get this far. So this time we're starting with moles of N2O5. That's our 0.5 number. And we're trying to go to moles of O2 so that we can then go to grams of O2. The first step, though, is to use the molar ratio, that 5:2 ratio from the balanced equation, to get from moles of N2O5 to moles of oxygen. And then going from moles of oxygen to what it's actually asking us for this time is grams of oxygen. That's actually something that we've done before. So if I want to go from moles of a substance like oxygen to grams of oxygen, hopefully you remember that we're going to go to the periodic table, right? And we're going to see what a mole of oxygen weighs, and that should be 32 grams. So it's just 16 from the periodic table times 2. So now that cancels moles of oxygen, and it does in fact leave me with grams of oxygen. So now I just have to do 0.5 times 5, which gives me 40 grams of oxygen needed. And I'm going to say 40.0 to keep the 3 significant figures that my original 0.500 had. Okay. All right, and then next up we have one where you have to come up with your own balanced equation. So we're talking about burning acetone, C3H6O. So see if you can come up with that balanced equation. All right, so there's our balanced equation for burning acetone. Now this one's a little bit different. It's not that different. This time we're starting with 225 grams of CO2, and we're trying to go to moles of acetone. So starting with 225 grams of CO2, we know without any sort of planning, we definitely have to get rid of grams of CO2. Now, we might be thinking, all right, but we need to know moles of acetone, so that goes on top, right? And the problem is we don't really have a relationship between grams of CO2 and moles of something else, right? In this case, acetone. But what could we go from grams of CO2 to? Right? Hopefully you said moles of CO2, because we know we can use the periodic table for this part. And then from moles of CO2, I'll fill that number in just a second, but from moles of CO2, we can then go, using the balanced equation like we've been doing these last few problems, to moles of acetone, which is what the question is asking us for, right? Okay, so that ratio, the moles of acetone, would be 1 from the balanced equation, right? Because there's just an implied 1 out in front here. And then the moles of CO2 would be 3, again, from the coefficient there. And then the only other thing we have to fill in before we plug in the calculator is the number from the periodic table for CO2. So 1 mole of CO2, if we go to the periodic table and we add up 2 oxygens and a carbon, should be about 44.01 grams. Grams of CO2 cancels, moles of CO2 cancels, and we're left with moles of acetone. And then we plug this in the calculator. All right, and this gave me 1.70 moles of C3H6O. Okay. All right, let's flip the page and try one more. It says how many grams of fluorine gas would be needed to fully react with 10.9 grams of gallium chloride. So fluorine gas is Brinkelhoff, so it's F2. Gallium chloride, gallium is +3, so that's going to give us GaCl3, and it's single replacement. And it does happen. It's not going to be a no reaction. I'm not going to ask you any stoichiometry questions where it's like a trick question where the answer is a no reaction. So this is a reaction. Fluorine does replace chloride, and it's going to give us gallium fluoride, which would be GaF3 plus Cl2, and then we would just have to balance with a 3, a 2, and a 2, and a 3. There we go. All right, and now we're ready to do the actual problem. Go ahead and see if you can set this one up on your own. This one is a grams to grams problem, but the steps are pretty much all the same. Okay, so here is our setup. We're going to go from grams of gallium chloride to moles of gallium chloride. That's the only thing we can really do from grams. And then we're going to use the balanced equation to go from moles of gallium chloride to moles of fluorine, because we have to go to moles of fluorine before we can go to grams of fluorine. All right, and then finally, we're going to go from moles of fluorine to grams of fluorine. All right, so if we start with the mole to mole ratio in the middle here in terms of filling these numbers in, that just comes from the balanced equation. So we have a 3:2 ratio when it comes to our mole to mole ratio. So 3 moles of fluorine for every 2 moles of gallium chloride, right? And then with our mole to gram or gram to mole ratios, it's always going to be 1 mole. And then we go to the periodic table, and I'm going to take 3 chlorines and 1 gallium, and that's going to give me about 176.07. Okay, and then we're going to do the same thing over here with fluorine, F2. So 1 mole of F2, it's just going to be 19 times 2, so that's going to be 38 grams of fluorine. And that cancels everything except for grams of fluorine, and it should result in an answer of 3.53 grams of fluorine. All right, and then the very last thing I want to show you here down below is this is basically just a diagram for how these problems work. So in terms of planning out these problems in the future, if you want to consult this little diagram, basically what we're saying here is we can always go from moles of substance A directly to moles of substance B. And the way that we do that, the way we do this is using the balanced equation, right? So I'm just going to say EQN is what allows us to go from one to the other, right? We just use the molar ratio. And then we can always start with grams of A, if that's what we're given, and go to moles using the periodic table, right? Just like we did up above. And then if we have moles of B, we can also take that to grams of B if we need to, again, using the periodic table. So this little diagram is going to be really helpful for us as we move forward in stoichiometry, because this is about as long a problem as we'll see, going from grams of substance A, which in this case was gallium chloride, all the way to grams of another substance in the balanced equation, which in this case was fluorine.